Good afternoon. My name is Neil Vickers. I'm from the University of Utah, and today I'll be talking about field evaluations of atmospheric turbulence and effects on female mosquito flight activity. I don't need to tell today's audience that the world's deadliest animals, female mosquitoes, at least according to this particular graphic, utilize a number of sensory cues to locate potential hosts in order to acquire a blood meal. These cues include carbon dioxide, humidity, skin odors, and temperature. And they're considered to be passive scalar cues because once they are released or emitted from a substrate, they are primarily transported and distributed by prevailing air or wind currents. Now, many laboratory studies of female mosquito behavior occur in relatively small bioassay chambers or wind tunnels with very smooth laminar flow, such as an example of which is shown here. And so a scalar released into laminar flow basically will result in a ribbon plume, a homogeneous ribbon plume, which doesn't deviate to one side or the other. It just moves directly in a straight line with the flow. If we place an object upstream of a scalar plume release point, that object is going to create eddies and turbulence in the moving airstream, and that is going to impose on the scalar a structure, a fine scale structure. And so a female mosquito navigating in this plume, say of carbon dioxide, is going to encounter fluctuating concentrations of the carbon dioxide as they navigate upwind, which they are perfectly capable of doing under wind tunnel conditions. However, in the field, the distribution of a scalar cue, such as carbon dioxide, is affected by atmospheric eddies that result in larger scale turbulence. And you can see that in this image here. So there's the fine scale of the structure, which is due to small scale turbulence, and then these large scale meanders in the scalar plume are caused by larger scale vortices and turbulence. So the female mosquito navigating upwind has to not only deal with the fine scale intermittency, but large scale meanders and vortices which cause these shifts in the plume. And Van Gogh realized these, or recognized this atmospheric turbulence, as you can see in his famous picture or painting Starry Night. So the primary goal of the study was, given that we know very little about the wind conditions in natural habitats that transport and shape the distribution of scalar host cues and the limits that these conditions might impose upon female mosquito behavioral responses, the idea was to characterize field wind conditions associated with female mosquito host-seeking behavior. So in order to do this, we partnered with the Salt Lake Mosquito Abatement District to measure wind conditions in areas where traps are typically placed to monitor mosquito populations. Now, these included flat, open areas around the wetlands surrounding the Great Salt Lake, northwest of the airport, and also urban habitats within Salt Lake City itself. In wetland habitats, the species that were primarily present or that are collected in these regions are Aedes dorsalis and Culex tarsalis. This image is a field site, taken at a field site that's pretty typical of those that we utilized in the wetlands over these past few years. And you can see this relatively flat, and there's abundant fresh water and brackish water in this region, which means that the mosquito populations are quite high. We employed a sonic anemometer, which is shown here, and the head stage of this device transmits ultrasonic pulses that are emitted from one transmitter to a receiver, and the time delay in receiving those pulses enables a calculation of the turbulence, and from those data that are collected, we can extract what's called the turbulent kinetic energy, which is the measure of the turbulence in the airstream. And these data can also be used to calculate the mean direction of flow, which is the horizontal direction of flow. The anemometer is placed in close proximity to a carbon dioxide emitting trap, which is equipped with a BG counter. So there's a trap which is sucking the mosquitoes in, and there's a counting device which registers the number of mosquitoes caught during 15-minute periods. So these data were collected over a single night, and mosquito activity was recorded primarily between sunset and sunrise, which is as you'd expect it to be. And we're looking at turbulence, mosquitoes, number of mosquitoes, and wind. And we can see some correlations between the turbulence and the wind magnitude and the number of mosquitoes that are being caught. And so things are relatively quiet initially after sunset, but they begin to ramp up, and there's a period of trap captures. And these are correlated with reduced turbulence, so a lower turbulent kinetic energy, and also a reduced wind magnitude. Wind picks up, and there are no trap catches during this period, and the turbulence is also increased during this period as well. This is followed by a dip in the wind speed, and we see that there is another bout of activity, which is also correlated with a lower turbulence measurement. Finally, as the night progresses, we enter a phase where the wind magnitude is relatively low, and the turbulent kinetic energy fluctuates somewhat variably, but this is correlated with a fairly robust number of mosquitoes being caught. You can see that in general, both turbulence and wind magnitude vary quite considerably, both during the day and the nighttime periods. If we look at a summary figure of the numbers of mosquitoes that are caught at specific turbulent kinetic energies or turbulence and wind magnitudes, we can see that most of the activity in terms of the turbulence is centered around 0.5 to 1 meter per second for turbulence, and anything above 2 meters per second in terms of wind magnitude really reduces the numbers of mosquitoes that are trapped or registered by the counter. In urban habitats, the following species were primarily present: Culex tarsalis again, Culex pipiens, Culoceta incidens. We know that Aedes syriensis is around, and we were trying to catch some of these, but unfortunately we did not. This is the same setup that we used in the open areas around the Salt Lake, in the wetland areas. It's a sonic anemometer and a trap with a counter on top of it. This is actually in my backyard. Because of COVID-19 last year, we actually had to get permission to do field research in my own backyard, but it did come with the benefit that we were able to have a beer or two while we were out trapping the mosquitoes. Traps were monitored only during the evening hours, and you can see that we registered mosquitoes coming into the traps during periods where we were also measuring the turbulence and the wind magnitude after sunset. So again, following sunset, you get activity. Now, one of the first things that you'll notice about these data is that although there's some variability, the variability around the mean is much, much lower in turbulence and wind magnitude, and the wind magnitudes themselves and the turbulence, the magnitude of the turbulence is also about an order of magnitude lower than what we were seeing in open field conditions. So to summarize our observations of wetlands or open areas versus urban canopied habitats, we make the following observations. The turbulence in the wetlands or open areas, open field, varied from 0 to greater than 5 meters per second. The wind magnitude varied from 0 to over 8 meters per second, which is a very fast wind speed. Trap catches tended to occur around about 0.5 to 1 meter per second in terms of turbulence, and wind velocities of around 1 to, from about 0.5 to 2 meters per second, so around about an average of 1 meter per second. In the urban habitat, canopied habitat, turbulence was much lower, was only reached barely above 0.4 meters per second. The wind magnitude was often only a little bit, at the most above a little bit, at half a meter per second. And the trap catches typically occurred when the turbulence was at 0.1 meter per second on average, with a wind speed of around about 0.2 meters per second. Now, you've probably noticed that as you were looking at those data, that wind magnitude and turbulence are correlated, and larger wind magnitudes are associated with higher turbulence. And mosquito activity primarily occurred within this range. So you can see this is a bounded range centered around about half a meter per second in turbulence and about 1 meter per second in the wind. These are data from the wetland habitat, trap catches in wetland habitat. So this is the range of turbulence and kinetic turbulence and wind magnitudes over which trap catches occurred. And for reference, this is where we measured in a wind tunnel, the wind tunnel that we typically use to characterize behavior, where what the wind magnitude and the turbulence was within our wind tunnel. And you can see right here that this is very low. In fact, this range that's represented here, we don't capture any of the turbulence that occurs in the field when we're seeing mosquito behavior. So we want to use these data to inform laboratory behavioral studies. So what do we want to do next? What are our next directions? Well, we want to do more fine-grained analysis of the wind conditions, because what we really need is instantaneous field wind conditions during mosquito flight. So when the mosquitoes are actually flying and we can record them flying, what are the instantaneous wind conditions? And we also want to replicate field-type wind conditions, turbulence and magnitudes in the laboratory. So how are we going to do this? Turbulence is chaotic. How can we recreate and control turbulence in a wind tunnel? So we are using what's known as an active grid, and the active grid controls turbulence, range and fluctuations by coordinated opening and closing of individual paddles. So here's a subset of the paddles that are used and placed in the path of the airflow, and these can be opened and closed individually to create turbulence within the moving airstream. And this is the full array of 60 paddles that are fully open in this particular picture, but that are placed within a wind tunnel. So how do we use this? Well, we use this to generate turbulence, and I can illustrate that with these smoke plumes. So this is the case where all of the paddles are open, and so you see this filamentous plume, and it's similar to that fine-scale structured plume because there is a little bit of fine-scale turbulence, but this is moving downstream. In this depiction below, we've imposed eddies, turbulent eddies on the moving airstream. So you can see these repeated structures that we're now able to generate with the active grid. So we believe that the active grid is going to give us insights into the behavior of mosquitoes and what they actually do when they're in a field setting. So hopefully we will be able to recreate what mosquitoes are doing under real starry nights. So I'd like to thank our collaborators in this endeavor, Marcus Hultmark and his graduate students and undergraduates at Princeton University have been building the active grid. Kirsten Meredith, graduate student in my laboratory, who's funded by the Pacific Southwest Vector-Borne Disease Association, and Ari Faraji and Greg White at the Salt Lake City Mosquito Abatement District. And if you have any questions, don't hesitate to contact me, n.vickers@utah.edu. Thank you.